LiDARs are amazing sensors capable of telling the distance to objects with very high precision. While their cousins, radars, use radio waves to estimate the distance to objects, LiDARs use, you guessed it, lasers, trading off the maximum distance for precision. In today's video, you will learn how to write a program that interacts with an actual LiDAR sensor, the world's coolest and accessible sensor. By the end of the video, you will be able to get the data from the sensor and visualize them in real time. As always, we're going to use Docker, Dev containers, CMake, gRPC, and there's a video for every single topic that I just mentioned. And a special guest of today, something called Yocto project. Yocto is a really cool framework that we can use to build our own custom-made Linux images. The working principle of a LiDAR is very simple. Luckily, I actually have a LiDAR with me and we can have a closer look. So this is a very low cost, very accessible LiDAR sensor. It spins like this, and while it is spinning, it shoots out infrared laser, so we can't see it. This laser beam will travel in a straight line. Whenever it reaches some object, part of the energy is reflected back. And this energy is captured by this other sensor here. So this is actually not a sensor, this is a light emitting diode, and this is a light receiver. And because we know the speed of light and we know all the distance that the mechanism has, we can factor out with some equations the total travel distance. We call this time of flight. And then we can tell almost exactly the distance to the object. The reason it's possible to compute, let's say, these really fast timings is because the manufacturers use very highly specialized chips and transceivers that are able to tell exactly or almost exactly when every laser beam was shot and when it was captured back, and then we can tell based on this time difference and the speed of light, we can tell the distance. Okay, so we know how it works if we want to shoot a single laser beam. If we want to cover, let's say, a region around us, all we have to do is what this manufacturer did, just spin it. So if I turn everything on, this will automatically spin and it's going to keep shooting lasers all over this rotation. After some time, we're going to have a lot of distances on the surroundings, pretty much covering the distance of every object in the 360 plane around us, and that is cool. Actually, there are two ways to do this. One way is to spin the whole mechanism, so we spin the laser and the receiver together, so they go together like this. Or you can spin a mirror, and this is actually how most of the high-end manufacturers do. They actually spin a mirror because it's less, let's say, it's less stressful, but they have to make a really good and precise mirror for that. Nowadays, there are dozens of types of LiDARs. Some of them specialize in short distances, other long distances. Some of them have wider angles, others narrow angles. Quite often, they are much more expensive than other distance-telling devices, such as radars, ultrasound, or other technologies, due to the mechanical precisions of all the parts that comes inside the LiDAR. This is very precise, high-end machinery that you have to use to come up with all the mechanical parts. But luckily, things have been changing lately. There was an introduction of something called solid-state LiDARs, which are LiDARs without any moving parts. This already made them extremely more accessible, aka cheaper, than the mechanical counterparts. Unlike conventional 3D mechanical LiDARs, which are usually LiDARs that cover 360, 180, plus some vertical coverage, so it's actually a full 3D cone, let's say. Solid-state LiDARs focus on the region, so there is very often actually a region of interest that they cover frontwards. So they don't usually go spinning, rather they have some kind of mechanism that focuses on a specific area. It's like you're aiming towards something, which of course is a bit of a disadvantage. So often we want to have as much field of view as possible, as much coverage, as much of area as possible. But very often having a focused area, it is really sufficient for a lot of applications. Just to give you an idea on the costs of each type of LiDAR. So the one we just saw in here, it's a very low cost one. I think it's the cheapest one even, that is reasonably effective. This one costs around 100 euros. It's a two-dimensional LiDAR. It covers all this plane, and it has no mirror. An equivalent industrial grade LiDAR with similar specs but higher precision would cost at least 2,000 euros. Okay, let's get serious. This is a solid state LiDAR. Ignore the thing in the top. You can already tell by its appearance that it has some of a focus area, so everything that comes in front of it, it's scannable. Now that you're an expert in LiDAR technology, you might be wondering, what are they used for? There's a good amount of applications out there. Autonomous robotic mapping, my favorite. Autonomous vehicle driving, drone surveys, industrial mechanical safety, aerospace, and much more. All in all, LiDAR falls into a domain category called computer vision. So essentially, if you want to give, let's say, eyesight to your computer or to your machine, LiDAR is very often a solution for you. Of course, they are comparable to actual cameras, RGB cameras, infrared cameras, but the fact that they give you very precise distances over an area or a field gives them a lot of advantages in a lot of cases. Most of the time, cameras or a combination of different cameras can give as best as they can estimates of distances, while LiDARs give you very good actual measurements. If you're into a domain that requires you to solve, let's say, geometrical problems, so distances, shapes, let's say localization where you are at any time, so having a LiDAR to tell you everything about your surroundings, all the distances, is really convenient. Okay, the time has come to get some stuff done. Let's get practical. When you want to make a software that interacts with a piece of hardware, a good starting point is naturally the vendor. In 99.9% of the cases, they will provide some kind of SDK, aka software development kit, so that you can use to interact with their devices. And of course, it wouldn't be different for this LiDAR right here. So let's see how this works. We go to the vendor webpage. So this LiDAR is manufactured by SlamTech. They also make different versions of different precisions of LiDARs. So yeah, if you wanna, you can see more details on other products. But what's important for us is those two pages right here. I know already this is where they host their SDK, software development kit, and we can use that to write code to interact with this device. And it's actually a GitHub page. So right here, it's reasonably maintained 3 months ago for the last commit to the master. I think it's okay. And yeah, from this point forward, what I do, I just look at the documentation. And one thing I really like to do before maybe even reading the documentation is to look for the example. And this is very common also that they post some examples for you. So if you go to app, in this case, ultra simple, I think they really want you to go to that first. We have an executable that we can compile and run, and this is likely already to work. And if I connect my LiDAR to some computer and start this program, it's probably gonna already tell me, hey, it works, here's the data. Remember, our focus is to get distance measurements. This is the most important part, is that we use the LiDAR to read out the distances around us. So this is the main goal. It doesn't matter extra features that this sensor might have. It doesn't matter, like, let's say the spinning speed or the frequency. It doesn't matter much. It matters that we somehow use a code to get the data. Now, it can happen sometimes that this code is too generic. So this one, for example, looks like it works for Apple, Windows, and Linux. Maybe we don't have to think about this. So in practice, this is really like a reference for us. So this is a starting point, and we should just look at the main parts and try to make use of them in our own code. And it's not very surprising that we may need even to fork the repository and do some changes. Thankfully, I did this already. So I had to do a fork to be able to use this project as a CMake project, for example. So if you look at top repository, there's no CMake list, there's no CMake project, and I was really bothered by this. So I made a fork that converts this whole project to a CMake project. And yeah, life is, I think, easier. Never forget also that if you are forking something, keep in mind about the licensing and all the restrictions and constraints and freedoms and benefits and whatnot. Okay, we have now a reference code to use to talk to the sensor. Let's do things ourselves, shall we? I have prepared a repository that already uses this reference example, this ultra simple example that the vendor provided, and I stripped away everything that was extremely not necessary. Moreover, I do use the forked version of this repository that simply adds the CMake lists, so it converts effectively the project to a CMake project. And this makes my life easier to use in another part for other applications. So this is the forked version, this is the CMake, you can have a look, it's right there in the GitHub repository. I'll put a link in the description. Now let's have a look at the, let's say, bare minimum application to make this sensor work. So this is pretty much the same code you see in the Ultra Simple, but all the generic stuff is gone. This is actually using their provided driver code, and this is how they create their objects and then allow your sensor to be connected. So there's something called a channel, there's something called LiDAR driver. It's not difficult. If you look, you don't have to look deeper, that's pretty much it. So it creates a serial port, and then we have to give it a port. Then it prints out information. This could have also been left out even. We can set the speed of this rotary motor, and we can start the scan, and then we put in some kind of loop a grab scan data HQ, and then there's something else we can do, and looks like this is enough. Well, let's just compile it. Now I'm gonna reopen this repository in the container. So this, let's call it the client, or today's experiment was completely done in a development container, so I can build this inside a container. A very special thing has to be mentioned here. If we look at this hardware that I created with my own hands, you're gonna see here a Raspberry Pi 5. This is an ARM architecture processor, ARM64, and I intend to deploy my code into this architecture. So we're not doing code that runs on a laptop anymore. Today's video is really a really big step towards something really great. We're gonna make code, compile code in a laptop, and have it run perfectly fine in another machine. You like that? I have to say though, if you want to learn more about this, we're gonna have to leave it for another video, because otherwise it's gonna be really big. Today, let's focus on the software part, not the deployment part. But keep in mind that there's a way to build an application in your laptop in a dev container and easily deploy in a very different machine without even cross-compilation concerns, and it's just gonna work. Alright, let's get back to the code. This is once more that very simple example. Ideally, we just need to run it, but I'm gonna add a few just look to when we start this. And a very important thing, it's a little bit about deployment, but let's not go too much into detail. In the CMake file, we have a list of things to be installed. So basically those are binaries, and I use something called CPack. CPack is like CTest. It's, let's say, a module from CMake that allows us to package our code into a distro-specific packaging system. For example, I am packing up to RPM, which is Red Hat-like distributions. All I had to do is this. So CMake knows that all install targets, every target that we labeled as install, will belong to the package. And in the end of the process, I will start right away. In the end of the process, we're going to have a RPM file with a specific name and the specific packaging strategy. It's possible to process the file in the package manager of your target system. So I just produced this binary, and right now I'm going to place this code into this Raspberry Pi. By the way, I turned it on, so everything is online, and I also put my network in the same network of this Raspberry Pi. It generates a hotspot, I connect to it, and then we are in the same network. All that matters is that there's a way I can generate a package, and I can copy paste that into the Raspberry, and I can, from the Raspberry, install a package and run an executable. So this is the way I created to port this code from a machine to another machine. Alright, so it is CPacked. I will deploy. It's a very simple VS Code task, just to use RCP, which is a SSH copy. And now I will log to the Raspberry Pi. I was logged in, but I will log again. And I should see this package right here. That's this too. And I will reinstall it or install it if it's the first time. And all these binaries that I compiled in my dev container are already able to be run in the Raspberry Pi. So one of the executables is called main test. I have to tell the device, this is the serial device connected to the LiDAR. And it looks like it worked. Look at this. Hello YouTube. And just to prove prove live that it's really the same code, I will just cpack it once more. It is packaging the binaries. I'm gonna redeploy it, still the older version. Hello YouTube. But now I'm gonna reinstall. Yep, hello YouTube, it's really this code. So you can see I'm developing in a laptop. It just works in the Raspberry Pi. And I can use, of course, all the facilities. So here I have clean tidy, I have auto completion, I have everything as if I was deploying to a machine that has all these development features. So this is really neat. Okay, so this code works. This is a very simple code. Looks like we are getting data and it's going somewhere. Looks like these nodes. And looking good. Now let's get to a very important topic, which is abstraction. Now, this code that the vendor provided is too low level for my taste. So I immediately, when I see it, I immediately think, okay, this should be only one function. And all the nasty stuff should be hidden or abstracted inside a class. So whoever uses this has a more easy life. Or even, let's say I plug in multiple LiDAR devices in different serial ports. Wouldn't it be much simpler to have a class that abstracts this whole procedure of starting up LiDAR and getting the data? If I just created an object and have an array of them to each different port. So this is the thinking about devices and hardware. Is how to think of them as actual classes. Not to forget about testability and the possibility to mock them. So this is where I want to lead us towards right now. So thinking about interface, this is what I think it's a good interface to communicate with the LiDAR. So the way I would develop this client code to communicate with this LiDAR is by defining firsthand an interface. So this is an interface class, and I explicitly express that with this I. So if someone uses this, they should know, or they should be aware that this is an interface, so no implementation whatsoever inside the class, only virtual deleted functions like this. And a very important thing about the interface definition is that we can also define our data type, or at least a data that is meant to be used in the. So right here, this is a 2D LiDAR, so all I have per, let's say, scan point, I should have a coordinate expressing where this is in relationship to the origin of the sensor. So this X, Y, it should be part of the interface definition. So whoever uses this LiDAR as an interface should also be aware and should also be able to use DIP.2 as a data. Naturally, this is some of our functions, or maybe more in the future, they should use this that I just defined. It would not make sense if I had this defined and not use it in my methods. So only define in the interface what you're going to use in the interface. No need to do it somewhere else. Now that we have defined an interface, we can define implementations. And one thing that I've learned in the past few experiences is to define simulators. So simulators are derived from the interface, and they implement, let's say, very simple, very trivial functions so that we can inject simulators into our more complex components. Imagine if I had a system that was meant to use LiDARs as part of the system. Let's say the system is a localization system. So it's a robot that looks at multiple LiDARs and they should do something with the LiDAR data. Imagine if I wanted to test software components of the robot without having to plug the LiDAR, and also not necessarily needing to mock it. I actually want to plug in a simulator. This is how we do it. We define an interface, we derive this interface with a simulator object, and then we just implement the functions in a very simple way. This was done right here. So here I have defined the sim LiDAR, and I also have implemented this method. So all it does, it prints out functions being called, whenever they're called. To get scanned, for example, I try to simulate more or less the behavior of this actual device. So it takes roughly 0.1 seconds to get each scan, so I wait a little bit and then prints out some dummy data. Look at the final application, how clean it is. I can make a pointer of the type LiDAR, so the type of the interface, and I can call my function or my program, and depending on the argument, it's gonna instantiate either the simulator device or the actual device. So I can have the same program configurable so that it either simulates or not. And this is really convenient because sometimes we don't have the LiDAR, but we want to use something close to the LiDAR, or at least a mock, so to speak, component, so that we just plug it in and see colors, how they're dealing with the LiDAR. It's almost like a mock, but it has more deeper purpose in integration testing. Now back to the interface. We have defined an interface, we have an implementation as a simulator, and what does the actual RPLidar, so the concrete implementation that actually talks to the sensor, should look like? Of course, it inherits from the interface and it implements all the methods that we came up with. And this is where the actual SDK is supposed to be used. So whoever uses the RPLidar class should not be concerned about how it works. Because remember, imagine all they know is the interface. They should not care about this guy. They should care about this interface and the contracts and the methods that the interface exposes to the user. This driver should not appear in the client code or whoever uses this component at all. All they should be aware of is the interface. I can't stress this enough. This is very important for testability and for good quality code. So this is how the implementation looks like. And if we look inside the class, everything, all implementation details are supposed to be here. So baud rate, this is a serial ports configuration. We probably want to do some conversions because the data that comes out of the drivers are not our interface definition, of course, they're something else, and then we have to convert it to this interface that we defined. So whoever uses the interface is really having a good life. Whenever we instantiate the object, we want to check serial port exists, we want to check, actually we check in the initialize. Yeah, well, we have to check if things in the lower level are working fine. And initialize, this is where we use this main test code. So all this initialization part, they are present in the init method. Some printouts, not really necessary, but somewhat important. Yeah, basically just starting up or actually getting the data, which is get scan. So this is a method defined by our interface, and we implemented like this in the LiDAR. This is where I took the infinite loop as a reference. So we have this vendor specific types and vendor-specific ways of use, and we just call them. But at the end of this, let's say low-level calls, I want to convert back to this high-level interface-defined data. So I create a function to convert this data nodes to a vector with all the points, all the points that the LiDAR is spitting out. Here's where I convert to actually X and Y coordinates. Also took for an example from that code. Yeah, so this should implement this, and whoever uses this should not care much about, and this is what matters. So this is separation of concerns, single responsibility. So this is a clean code at its best. Okay, so we have simulator and everything else. Let's look at the actual code. Let's say the final, polished, well done, made, class-driven, object-oriented program. This is how it looks like. We define a LiDAR interface, unique pointer. I don't plan to share it, so I already used it. You can have used a raw pointer, it doesn't matter much. And look at this. Depending on what armies we give to this program, we can select runtime. Are we going to use a simulator or not? And simply, this is a silly contract. If we type sim in the program, it's going to use the simulator. If we type the port, we check if it exists, and then we instantiate the concrete implementation of the LiDAR with the given port. So see how the interface definition allows us to be flexible like this, and the calls are really simple. I call a niche, given the contract that it should be aware of at least. Set a motor speed, and this is just gRPC specifics to publish, or should I say to host a server that whoever connects to the server will be able to fetch the data as well. A little bit more on gRPC, the way I implement it is there is a class that abstracts away all this gRPC stuff. There's a thread specific also future async running inside it. Doesn't matter much for today's video. And if there's a queue and I push to the queue, and then whoever subscribes to this gRPC server, it's a streaming, will get the latest data. That's all that matters. The data is actually taken by this function, getScan. This is a vector of points to the plan. I also print out the points, and then if something happens or I quit or whatever, I stop the server. Actually, this is kind of silly because this loops never ends. But anyway, the idea was the important part here. Alright, the main takeaway here, thinking about devices as objects. So the LiDAR is a class, there is an interface. If I define well the interface in a very minimal, only required, simple manner, whoever is going to use this interface will have a really good time and very intuitive usage of the interface. This is the very important part. It's a LiDAR, I want to get data and I want to start the LiDAR. So this is how the interface should look like, and all the details should be hidden in the implement. This is really important. It's a really important concept. I can't stress enough. All right, let's see how this works. I have already compiled and deployed to the Raspberry Pi. All I'm gonna do is open the terminal and call this executable, so this RP Publisher app, which is the high-level usage of this RPLidar SDK. Yeah, if I don't give it arguments, it's gonna complain to give arguments. It works with the simulator, and the simulator simply spits a few points, or it works and I tell which device is connected, just like that. And I'm gonna put this aside for now, and I'm gonna bring a new cool window. This, people, is the same application that I use for the 3-body problem video, exactly the same. It's just an OpenGL server that listens for gRPC connections, and whatever and whoever publish or post data to this server will have its stuff rendered, just like that. Pretty much like the 3-body problem video. Those are basically just points, and the LiDAR, this application is in real time publishing the data to my server. And we can see here, if I put the hand, I can block the front, I can block the right side, I can block the left side, and I can block the behind. And the cool thing is, this is real measurements, so every distance here is given in meters. Yeah, I can't actually draw a line here in the application, but you can trust me. And I'm just gonna walk around so you can see me moving in the room just by looking at this moving dots. Yes, I'm at the right side of the sensor, and now I'm going to get back to the video. And as you have seen in the introduction, we can move it around. So right here, I'm rotating it. It's totally portable. And yeah, it just works. It's a Raspberry communicating with the LiDAR sensor with a program that was developed in a dev container, cross-compiled to the ARM architecture in a MacBook, running an application to communicate with the LiDAR. This is really cool. Let's put this away. Now, I have to say, whatever involves LiDARs have my deepest love, because I really enjoy this kind of technology. I think the idea of giving eyes like this to a machine or a computer is really, really fascinating. And one of the applications that I plan to work in the future of this YouTube channel is something called SLAM, Simultaneous Localization and Mapping. SLAM is an algorithm that looks at this, let's say, two-dimensional floor plan, and it incrementally builds a map, and it knows while building the map, it knows how much you have been moving. So if I move like this, it's gonna be very smart interactively, increment the missing parts until I have a complete floor plan. Because of course, if you look at this, a lot of stuff is missing. Visually, we can tell some stuff is missing. But if I move just enough to a side, I might be able just to fill this gap. And the SLAM algorithm allows us to fill this very nicely and very intelligently. And this is something I'm very passionate about. So today's video was different and special in this sense that it introduces something I really enjoy doing and teaching and learning about. That's it for this video. Thank you so much for watching. I hope you have enjoyed it. It might have been a too long video. I will try my best to make the following videos smaller or maybe cut them in parts. And once more, thank you for watching. I hope you have liked something. I hope you had learned something. We keep in touch.